Our universe is a place of profound mysteries. From the smallest particles to the largest galaxies, the cosmos beckons us to unravel its secrets. One of the most tantalizing puzzles lies at the intersection of the very large and the very small, the realm of quantum gravity. You might have heard about cosmic discoveries. It's the field where we explore the biggest questions about the universe. And guess what? Quantum gravity is a hot topic in this field. For centuries, physicists have sought a single, elegant theory that can explain all the forces of nature. This theory of everything would unite the macroscopic world of gravity, described by Einstein's general relativity, with the microscopic world of quantum mechanics, which governs the behavior of particles at the atomic and subatomic levels. But there's a catch. These two pillars of modern physics seem to be speaking different languages. Like trying to fit square pegs into round holes, combining gravity and quantum mechanics has proven to be a formidable challenge. Imagine a graceful waltz between two cosmic dancers, gravity and quantum mechanics. General relativity, the theory of gravity, paints a picture of a smooth, continuous space-time fabric that is warped by massive objects like stars and planets. This warping of space-time is what we experience as gravity. On the other hand, quantum mechanics reveals a universe that is fundamentally granular and uncertain at its core. Here, particles can exist in multiple states at once, and their behavior is governed by probabilities rather than definite outcomes. These two theories have revolutionized our understanding of the universe, but they seem to clash when we try to merge them. General relativity works beautifully on large scales, explaining the motion of planets, the formation of galaxies, and the expansion of the universe. Quantum mechanics reigns supreme in the microscopic realm, governing the interactions of particles and the behavior of atoms. The problem arises when we consider extreme environments where both gravity and quantum mechanics are expected to play a significant role. For example, at the center of black holes or in the very early universe. In these extreme conditions, the immense gravity compresses matter into incredibly tiny spaces where quantum effects can no longer be ignored. Here's the crux of the issue. General relativity predicts that space-time should become infinitely curved and dense at the singularity of a black hole, or at the moment of the Big Bang. Quantum mechanics, however, suggests that such infinite densities are impossible, and that something else must happen at these extreme scales. This fundamental incompatibility between general relativity and quantum mechanics is the driving force behind the search for a theory of quantum gravity. Physicists are striving to find a framework that can reconcile these two pillars of modern physics and provide a consistent description of the universe at all scales, from the subatomic to the cosmic. String theory, music of the universe. One of the leading contenders in the quest for quantum gravity is string theory. Imagine the universe as a grand symphony, and instead of point-like particles, we have tiny, vibrating strings. Just as a violin string can produce different notes depending on how it vibrates, different vibrations of these fundamental strings give rise to the different particles and forces we observe in nature. String theory proposes that these strings are incredibly small, far smaller than anything we can currently observe with our most powerful microscopes. In fact, they are thought to be curled up in extra dimensions that are hidden from our perception. Think of a garden hose from a distance. It might look like a one-dimensional line, but as you get closer, you see that it has a second curled-up dimension. String theory is a mathematically elegant and compelling framework, but it faces some challenges. One of the main criticisms is that it makes predictions that are extremely difficult, if not impossible, to test with current technology. For example, string theory predicts the existence of extra dimensions, but we have yet to observe any direct evidence for them. Loop quantum gravity, space-time woven from loops. Another promising approach to quantum gravity is loop quantum gravity. This theory takes the idea of a quantized universe to heart, proposing that space-time itself is not smooth and continuous, but is woven from tiny, indivisible loops. Imagine a beautiful tapestry woven from countless threads. In loop quantum gravity, space-time is like this tapestry, with each loop representing a fundamental unit of area and volume. These loops are incredibly small, on the order of the Planck length, which is about 10 to the minus 35th meters, far smaller than anything we can currently observe. Loop quantum gravity has some intriguing features. For example, it suggests that the Big Bang singularity might be replaced by a big bounce, where the universe contracts to a certain point and then expands again. This theory also predicts that black holes might not be truly black, but could emit a faint Hawking radiation due to quantum effects near their event horizons. Implications of quantum gravity. Unlocking the universe's secrets. Understanding quantum gravity would be a profound scientific breakthrough, with far-reaching implications for our understanding of the universe. It would not only reconcile two of our most successful theories, but also open new windows into the nature of reality itself. Unveiling the secrets of black holes. Quantum gravity could help us understand what happens at the singularity of a black hole, where gravity becomes infinitely strong. It might even provide insights into the nature of information and whether it is truly lost inside black holes. Probing the very early universe. A theory of quantum gravity would be essential for understanding the very early universe, just moments after the Big Bang. It could help us answer fundamental questions about the origin of the universe and the nature of cosmic inflation. New technologies and innovations. As with any major scientific breakthrough, understanding quantum gravity could lead to new technologies and innovations that we can't even imagine today. These could range from new energy sources to revolutionary computing technologies. Conclusion. The journey continues. The search for quantum gravity is a journey into the unknown. It is a testament to the power of human curiosity and our relentless pursuit of knowledge. While we haven't yet found a complete theory that unites gravity and quantum mechanics, the quest itself has already yielded profound insights and pushed the boundaries of our understanding. Thank you for joining me on this exploration of quantum gravity. I encourage you to keep asking questions, keep exploring, and never stop wondering about the mysteries of the universe.